Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Photodetector, PIN Photodiode and Avalanche Photodiode from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about a photoconductor. Secondly, a photodiode will be discussed, that is its schematic and variation of photocurrent density. Thirdly, PIN photodiode will be discussed. Next, we will also discuss about the avalanche photodiode. Lastly, we will discuss about a phototransistor. So students, let us start with a basic introduction about the module. There are several semiconductor devices that can be used to detect the presence of photons. These devices are known as photodetectors. They convert optical signals into electrical signals. When excess electrons and holes are generated in a semiconductor, there is an increase in the conductivity of the material. This change in conductivity is the basis of the photoconductor, perhaps the simplest type of photodetector. If electrons and holes are generated within the space charge region of a p-n junction, then they will be separated by the electric field and a current will be produced. So the p-n junction is the basis of several photodetector devices, including the photodiode and the phototransistor. Photoconductor. So this figure shows a bar of semiconductor material with ohmic contacts at each end and a voltage is applied between the terminals. So the initial thermal equilibrium conductivity is given by sigma naught equal to E multiplied by mu n n naught plus mu p p naught. If excess carriers are generated in the semiconductor, the conductivity becomes sigma equal to E multiplied by mu n multiplied by n naught plus delta n plus mu p multiplied by p naught plus delta p, where delta n and delta p are the excess electrons and holes concentrations respectively. So if we consider an n-type semiconductor, then from charge neutrality, we can assume that delta n equal to delta p. So we will use delta p as the concentration of excess carriers. In steady state, the excess carrier concentration is given by delta p equal to GL multiplied by tau p, where GL is the generation rate of excess carriers in centimeter minus 3 second inverse, and delta p is the excess minority carrier lifetime. So the conductivity from the previous equation can be rewritten as sigma equal to E multiplied by mu n n naught plus mu p p naught plus E multiplied by delta p multiplied by mu n plus mu p. The change in conductivity due to the optical excitation is known as photoconductivity, which is given by delta sigma equal to E multiplied by delta p multiplied by mu n plus mu p. So an electric field is induced in the semiconductor by the applied voltage, which produces a current. So the current density can be written as J equal to J naught plus JL equal to sigma naught plus delta sigma multiplied by E, where J naught is the current density in the semiconductor prior to optical excitation and JL is the photocurrent density, and it is given by delta sigma. If the excess electrons and holes are generated uniformly throughout the semiconductor, then the photocurrent is given by IL equal to JL multiplied by A equal to delta sigma multiplied by AE equal to E GL multiplied by tau P multiplied by mu N plus mu P multiplied by AE, where A is the cross-sectional area of the device. So the photocurrent is directly proportional to the excess carrier generation rate, which in turn is proportional to the incident photon flux. If excess electrons and holes are not generated uniformly throughout the semiconductor material, then the total photocurrent is found by integrating the photoconductivity over the cross-sectional area. Since mu NE is the electron drift velocity, the electron transit time, that is the time required for an electron to flow through the photoconductor, is given by Tn equal to L by mu NE. So the photocurrent from equation 6 can be written as IL equal to E multiplied by GL multiplied by tau P by Tn multiplied by 1 plus mu P by mu N multiplied by AL. So we may define a photoconductor gain as gamma photo as the ratio of the rate at which the charge is collected by the contacts to the rate at which charge is generated within the photoconductor. So we can write the gain as gamma pH equal to IL by EGLAL, which using equation 8 can be written as gamma pH equal to tau P by Tn multiplied by 1 plus mu P by mu N. The excess electrons will drift quickly out of the photoconductor at the anode terminal. So in order to maintain the charge neutrality throughout the photoconductor, another electron immediately enters the photoconductor at the cathode and drifts towards the anode. This process will continue during a time period equal to the mean carrier lifetime. So, at the end of this period, on the average, the photoelectron will recombine a hole. When the optical signal ends, the photocurrent will decay exponentially with a time constant equal to the minority carrier lifetime. From the photoconductor gain expression, we would like a large minority carrier lifetime, but the switching speed is enhanced by a small minority carrier lifetime. So there is obviously a trade-off between the gain and the speed. In general, the performance of a photodiode is superior as that of the photoconductor. Let us now discuss about a photodiode. A photodiode is a PN junction diode operated with an applied reverse biased voltage, and here we will consider a long diode in which excess carriers are generated uniformly throughout the semiconductor device. And the device in reverse bias configuration is shown in this figure, where the figure A shows a photodiode connected in reverse bias configuration, and the part B shows us the variation of minority carrier concentration with distance along the reverse biased PN junction diode. So let us now discuss the photocurrent density for the photodiode. Let GL be the generation rate of excess carriers which are generated within the space charge region. So these excess carriers move out of the depletion region under the influence of the applied electric field. That is, electrons move to the N region and holes move towards the P region. So the photon generated current density from the space charge region is given by JL1 equal to E multiplied by integral GL dx, where the integral is over the space charge region width. If GL is constant throughout the space charge volume, then JL1 is equal to E GLW, where W is the space charge width, and we may note that JL1 is in the reverse bias direction through the PN junction. So this component of photocurrent responds very quickly to the photon illumination and is known as prompt photocurrent. The excess minority carrier electron distribution in the P region is found from the diffusion equation, which is given by dn del square of delta np by del x square plus gl minus del np by tau n naught equal to delta of delta np by del t. Now we will assume that the electric field is 0 in the neutral regions. So in steady state, del of delta np by del t equal to 0, so that equation 13 can be written as d square of delta np by dx square minus delta np by ln square equal to minus gl by dn, where ln square equal to dn tau n naught. So the solution to this equation can be found as a sum of the homogeneous and particular solutions. So the total steady state solution for the excess minority carrier electron concentration in the P region is then delta Np equal to A exponential minus x by ln plus gl tau n naught. So the total electron concentration is 0 at x equal to 0 for the reverse biased junction. So the excess electron concentration x equal to 0 is then delta Np at x equal to 0 is equal to minus Np naught. Using the boundary condition from equation 16, the electron concentration is given by equation 15 becomes delta Np equal to gl tau n naught minus gl tau n naught plus Np naught, the whole multiplied by e to the power minus x by ln. So we can find the excess minority carrier whole concentration in the N region using the same type of analysis. So now using the x prime notation shown in this figure B, we can write delta Pn equal to gl tau p naught minus gl tau p naught plus Pn naught, the whole multiplied by e to the power minus x prime by Lp. So equation 17 and 18 are plotted in this figure below, where the steady state values are very far from the space charge region are the same as given previously. So the gradient in the minority carrier concentrations will produce diffusion currents in the PN junction. Diffusion current density at x equal to 0 due to minority carrier electrons is Jn1 equal to E dn d derivative of delta Np with respect to x at x equal to 0, equal to putting the value of delta Np over here and differentiating, we get E dn by ln multiplied by gl tau n naught plus Np naught. So equation 19 can be written as Jn1 equal to E gl ln plus E dn Np naught by ln. The first term in this equation is the steady state photocurrent density, while the second term is the ideal reverse saturation current density due to the minority carrier electrons. So the diffusion current density in the x direction at x prime equal to 0 due to the minority carrier holes is Jp1 equal to EJP LP plus EDP Pn naught by Lp. Similarly, the first term in the steady state photocurrent density and the second term is the ideal reverse saturation current density. So the total steady state diode photocurrent density for a long diode will be the sum of the two. That is, your JL will be equal to E GNW plus E GLLN plus E GLLP, which is equal to E V plus Ln plus Lp multiplied by GL. So the photocurrent given by this summed equation is the result of assuming a uniform generation of excess carriers throughout the structure, a long diode and steady state. So the time response of the diffusion components of the photocurrent is relatively slow, since these currents are the results of the diffusion of minority carriers towards the depletion region. So the diffusion components of photocurrent are referred to as the delayed photocurrent. So students, let us now discuss about the PIN photodiode. The speed of response of photodetector is very important in many applications. Hence, a quick generation of photocurrent in the space charge region is the only photocurrent of interest. So, aiming towards increasing the photodetector sensitivity, the width of depletion region should be made very large. This can be achieved in a PIN photodiode. So, the PIN photodiode consists of a P region and an N region separated by an intrinsic region. So, this figure shows the schematic of the PIN photodiode, and the intrinsic region width W is much larger than the space charge width of a normal PN junction. If a reverse bias is applied to the PIN diode, the space charge region extends completely through the intrinsic region. Now here, assuming that a photon flux of phi naught is incident on the P plus region, and if we assume that the P plus region width WP is very thin, then the photon flux as a function of distance in the intrinsic region is JL equal to E multiplied by integral 0 to delta GL dx equal to E multiplied by integral 0 to W over phi naught alpha e to the power minus alpha x dx equal to E phi naught multiplied by 1 minus e to the power minus alpha w. Now here alpha is the photon absorption coefficient. This nonlinear photon absorption is shown in this figure B. So the photocurrent density generated in the intrinsic region can be found by JL equal to E multiplied by integral 0 to W GL dx equal to E multiplied by integral 0 to W over phi naught alpha e to the power minus alpha x dx equal to E phi naught multiplied by 1 minus e to the power minus alpha w. So this equation assumes that there is no electron hole recombination within the space charge region, and also that each photon absorbed creates one electron-hole pair. Avalanche photodiode. The avalanche photodiode is similar to the PN or PIN photodiode, but in this case, a very high bias is applied to the avalanche photodiode in order to cause the impact ionization. Here, electron-hole pairs are generated in the space charge region by photon absorption, and due to the impact ionization, photon-generated electrons and holes further creates more electron-hole pairs. The avalanche photodiode now has a current gain introduced by the avalanche multiplication factor. The electron-hole pairs generated by photon absorption and by impact ionization are swept out of the space charge region very quickly. Now consider the saturation velocity is 10 to the power 7 centimeter per second in a depletion region that is 10 to the power minus 4 meter wide. Then the transit time is tau t equal to 10 to the power 7 divided by 10 multiplied by 10 to the power minus 4 equal to 100 picosecond. So the period of modulation signal would be 2 tau t, so that the frequency would be f equal to 1 by 2 tau t equal to 1 by 200 multiplied by 10 to the power minus 12 equal to 5 gigahertz. So if the avalanche photodiode current gain is 20, then the gain bandwidth product is 100 gigahertz. The avalanche photodiode could respond to light waves modulated at microwave frequency. Let us now discuss about a phototransistor. A phototransistor can be considered to be as the bipolar transistor having high gain performing the operation of a photodetector. So the schematic of the NPN bipolar phototransistor is shown in this figure. This device has a large base collector junction area and is usually operated with the base open circuited. So the figure B shows the block diagram of the phototransistor where the electrons and holes generated in the reverse biased base collector junction. These charge carriers are swept out of the space charge region, producing a photocurrent IL. So here, holes are swept into the p-type base, making the base positive with respect to the emitter. Since the base emitter becomes forward biased, electrons will be injected from the emitter back into the base, leading to the normal transistor action. So from figure B, we see that IE equal to alpha IE plus IL, where IL is the photon generated current and is the common base current gain. Since the base is open circuited, so we have IC equal to IE, so this equation can be written as IC equal to alpha IC plus IL. So solving for IC, we find that IC equal to IL by 1 minus alpha. So now relating alpha to beta, the DC common emitter current gain. So this equation, that is the previous equation, becomes IC equal to 1 plus beta multiplied by IL. So this equation shows that the basic base collector photocurrent is multiplied by the factor 1 plus beta, which the phototransistor amplifies. With the relatively large base collector junction area, the frequency response of the phototransistor is limited by the base collector junction capacitance. since the base is essentially the input to the device. The large base collector capacitance is multiplied by the Miller effect. So the frequency response of the phototransistor is further reduced. The phototransistor, however, is a lower noise device than the Avalanche photodiode. Phototransistors can also be fabricated in heterostructures. So the injection efficiency is increased as a result of the band gap differences. With the band gap difference, the lightly doped base restriction no longer applies. So a fairly heavily doped narrow base device can be fabricated with a high blocking voltage and a very high gain. So students, let us summarize what we have learned in this module. So firstly, we discussed about the photoconductor. Secondly, the schematic of the photodiode and the variation of photocurrent density, its expression was derived. Thirdly, PIN photodiode was also discussed. Avalanche photodiode was discussed in this module. And lastly, we discussed about a phototransistor. Thank you.